There is something quietly fascinating about looking into the deepest parts of space. Not just because of what we see, but because of what we don't fully understand yet. The farther we look, the further back in time we go. And somewhere along that journey, the line between observation and interpretation begins to blur just slightly. Tonight, we're going to explore one of the most advanced tools humanity has ever built to peer into that unknown, the James Webb Space Telescope. Not as a story of fantasy or speculation for its own sake, but as a calm, careful examination of what it shows us, what scientists say it means, and where, perhaps, the questions begin to quietly outnumber the answers. Before we go deeper, take a moment to settle in, wherever you are listening from tonight. And if you enjoy this kind of slow, thoughtful exploration, somewhere between science and curiosity, consider subscribing and let me know in the comments where you're listening from, because it's always interesting to think that while we're talking about the vastness of the universe, we're all sitting here on one small planet, looking outward together. Now, officially, the James Webb Space Telescope, developed by NASA along with international partners, is designed to do something very specific. It observes the universe in infrared light, allowing it to see through cosmic dust, and more importantly, to detect objects that are so far away that their light has been stretched or redshifted over billions of years. In simple terms, it lets us look further back in time than ever before. Galaxies that formed just a few 100 million years after what we call the Big Bang. Stars that may no longer even exist. Structures that, until recently, were purely theoretical. That's the official purpose. And in many ways, it has done exactly what it was built to do. Since its deployment, Webb has delivered images of staggering clarity. Galaxies layered upon galaxies, gravitational lensing bending light like a cosmic magnifying glass, and atmospheric signatures of distant exoplanets that hint at chemical compositions we are only beginning to understand. Everything, at first glance, aligns with expectations. The telescope is working, the data is flowing, the models are being refined. But as with many moments in scientific progress, the interesting part isn't just what confirms our understanding, it's what doesn't quite fit. Because almost immediately, some of Webb's early observations began raising subtle but important questions. Not dramatic contradictions, not anything that breaks physics overnight, but small inconsistencies, patterns that don't line up as neatly as expected. For example, certain galaxies observed by Webb appear to be far more massive and more structured than they should be at such an early stage of the universe. According to standard cosmological models, galaxies take time to form, gravity pulling matter together slowly, stars igniting over millions or billions of years, structures gradually evolving. And yet, Webb is showing us galaxies that seem already mature, at a time when, theoretically, they should still be in their infancy. Now, the mainstream explanation is cautious, and understandably so. Scientists suggest that our models may need adjustment. Perhaps star formation in the early universe was more efficient than we thought. Perhaps these galaxies only appear more massive due to observational effects. Or perhaps we are misinterpreting certain signals. These are reasonable possibilities. Science, after all, evolves through refinement, not sudden leaps to unlikely conclusions. But this is where it becomes interesting to pause and simply ask a question. If our models of the early universe are based on assumptions that are now being challenged, even slightly, what does that imply about the larger picture? Not that everything is wrong, but that our timeline, our understanding of how quickly complexity can emerge, might not be as settled as we once believed. And this isn't the first time something like this has happened. Throughout the history of astronomy, new instruments have repeatedly revealed things that didn't quite match expectations. When Hubble Space Telescope first looked deeper into space, it reshaped our understanding of galaxy distribution. When cosmic microwave background radiation was mapped in detail, it refined our models of the early universe. Each time, the response wasn't to discard science, but to expand it. So with Webb, we find ourselves in a familiar position, but on a much larger scale. Another point worth considering is how much of what Webb shows us depends on interpretation. The telescope doesn't see in the way our eyes do. It collects infrared data, which is then processed, translated, and rendered into images that we can understand. Colors are assigned, structures are enhanced, noise is filtered. None of this is deceptive. It's necessary. But it does mean that what we're looking at is not a direct photograph. It's a representation of data, and that raises a subtle but important thought. How much of our understanding of the universe is shaped not just by what is observed, but by how that observation is processed? Again, the mainstream view is clear. These methods are rigorously tested, cross-validated, and scientifically sound, and there's no strong evidence to suggest otherwise. But even within that framework, interpretation plays a role. Decisions are made about how to model distant galaxies, how to estimate their age, how to infer their mass and composition from limited signals. These are educated, evidence-based decisions, but they are still decisions. And when Webb presents us with something unexpected, those decisions come under closer examination. There's also the question of scale. Webb is looking at distances so vast that the light we observe has traveled for over 13 billion years. That means we are not just seeing space, we are seeing time itself. But time, at that scale, is deeply connected to our assumptions about cosmic expansion, dark matter, and dark energy. Concepts that, while widely accepted, are still not fully understood. Dark matter, for instance, has never been directly observed, only inferred from gravitational effects. Dark energy is even more mysterious, a force we describe mathematically, but cannot yet explain physically. So when Webb's data interacts with these concepts, it's not just about observing galaxies, it's about testing the very framework we use to describe reality. And this is where the tone shifts slightly, not into speculation without grounding, but into curiosity about the boundaries of what we know. Because Webb is not just confirming theories, it is quietly probing them. If galaxies can form earlier than expected, what conditions allowed that? If structures appear more organized than predicted, what mechanisms are we missing? If our interpretations rely on unseen components like dark matter, how confident are we in the assumptions built around them? These are not radical questions. They are the natural next step in scientific inquiry. But they do open a space, a small, thoughtful space, where alternative interpretations can exist, not as claims, but as possibilities to be examined. And perhaps that's the most fascinating part of all. Because the James Webb Space Telescope isn't just showing us the distant universe. It's showing us the edges of our current understanding, not breaking it, not disproving it, but gently pressing against it, revealing where it might stretch and where it might eventually need to change. So as we continue this journey, we're not here to jump to conclusions. We're here to observe carefully, to compare what is expected with what is seen, and to ask, quietly and thoughtfully, what happens when the most advanced tool we've ever built begins to show us things we didn't fully anticipate? As we move a little deeper into what the James Webb Space Telescope is actually revealing, it helps to slow down and focus on one of the central ideas that shapes almost everything we think we know about the universe: the timeline. Not just the age of the universe, often estimated at around 13.8 billion years, but the sequence of events that are believed to have unfolded within that vast stretch of time. Because Webb, in a very quiet and methodical way, is not just showing us distant galaxies, it is giving us data points along that timeline, and some of those points don't seem to land exactly where we expected them to. In the standard cosmological model, often referred to as lambda CDM, the early universe begins as a hot, dense state following what we call the Big Bang. In the hundreds of thousands of years that follow, matter cools enough for atoms to form. Then, over millions of years, gravity begins pulling gas together into the first stars, and eventually into the first galaxies. These early galaxies are expected to be small, irregular, and relatively simple in structure. Over time, through mergers and continued star formation, they grow into the large, complex galaxies we see closer to our present day. This framework has held up remarkably well for decades. It is supported by multiple lines of evidence, including observations from the Hubble Space Telescope and measurements of the cosmic microwave background. It's not just a theory in the casual sense, it's a deeply tested model that has been refined over time. But when Webb began observing galaxies at extreme distances, meaning extremely early points in the universe's history, it found something that has caused scientists to pause, just slightly. Some of these galaxies appear too developed. Not in a dramatic, impossible way, but in a way that suggests they may have formed stars more rapidly or assembled mass more efficiently than our models would predict. In some cases, galaxies observed within the first few 100 million years after the Big Bang seem to have disk-like structures, or levels of brightness that imply a surprisingly large number of stars already in place. Now, the immediate response from the scientific community has been careful and measured. One possibility is that we are overestimating the masses of these galaxies due to uncertainties in how light is interpreted at such distances. Another is that early star formation may have been more intense than expected, perhaps due to conditions in the early universe that we don't yet fully understand. There are also discussions about whether certain types of stars, so-called population 3 stars, which would have been massive and short-lived, could have contributed to this early brightness. All of these explanations remain within the boundaries of established science. They don't require rewriting the laws of physics, just refining the details. But again, this is where it becomes interesting to simply observe the pattern. Because this isn't just one galaxy. It's not an isolated anomaly. Webb has now identified multiple objects that seem to share this characteristic of early complexity. And when patterns begin to emerge, even subtle ones, they tend to draw closer attention. So we can ask, without jumping to conclusions, what if our assumptions about the rate of cosmic evolution are slightly off? Not entirely wrong, but incomplete. What if the early universe was capable of organizing itself into complex structures more quickly than we've modeled? And if that's the case, what conditions allowed for that acceleration? One idea that has been explored is the role of dark matter. In current models, dark matter acts as a kind of gravitational scaffold, invisible but essential in helping galaxies form by pulling ordinary matter together. But as we mentioned earlier, dark matter itself has never been directly observed. Its presence is inferred from gravitational effects, from how galaxies rotate, how light bends around massive objects, how large-scale structures behave. So if Webb is showing us galaxies forming earlier or faster than expected, it naturally leads to a subtle question about whether our understanding of dark matter's role is complete. Not whether dark matter exists, but whether we fully understand how it behaves, especially in the earlier stages of the universe. Another angle to consider is how we measure distance and time at these scales. The concept of redshift, the stretching of light as the universe expands, is central to how we estimate how far away an object is, and therefore how far back in time we are seeing it. Webb is exceptionally sensitive to infrared light, which allows it to detect objects with very high redshift values, meaning their light has been stretched significantly over billions of years. But interpreting redshift also depends on our model of how the universe has expanded over time. If that model has even slight inaccuracies, it could affect how we place these galaxies along the timeline. Again, not in a way that overturns everything, but in a way that introduces small uncertainties that become more noticeable as we look further and further back. And this is where the conversation becomes less about individual discoveries and more about the nature of scientific models themselves, because models are not fixed truths. They are frameworks constructed from the best available evidence that help us make sense of complex data. They are incredibly powerful, but they are also, by design, open to revision. When new data fits the model, it strengthens it. When new data doesn't quite fit, it creates an opportunity to refine it. Webb, in this sense, is not challenging science. It is doing exactly what science is meant to do, providing better data. But better data has a way of revealing the edges of our assumptions. And perhaps one of the most subtle but important aspects of Webb's observations is how they remind us of the difference between seeing something and understanding it. We can detect a galaxy, we can measure its light, we can estimate its distance and composition. But the story of how that galaxy came to be, how quickly it formed, what processes shaped it, how it fits into the larger cosmic narrative, that story is still being written. So as we continue, it's worth holding on to that perspective. We are not looking at definitive answers. We are looking at data interpreted through models that are themselves evolving. And in that space, between observation and explanation, is where some of the most interesting questions begin to form. Questions like, are we seeing the universe as it truly is, or as we currently understand how to interpret it? And if those two things are not perfectly aligned, how would we even know? Because when you're dealing with distances measured in billions of light years and timescales that stretch beyond intuitive comprehension, even small uncertainties can open the door to entirely new ways of thinking. Not radical shifts, not sudden revelations, but gradual, careful adjustments, the kind that reshape our understanding over years or decades rather than overnight. And Webb, quietly orbiting far beyond Earth, continues to collect the data that may guide those adjustments, one faint signal at a time. As we continue this slow and careful exploration, it becomes useful to shift our focus slightly, not just on what the James Webb Space Telescope is observing, but on how those observations are translated into something we can actually understand. Because when we look at those now famous Webb images, deep fields filled with thousands of galaxies, glowing clouds of gas shaped into intricate patterns, distant worlds hinted at through faint spectral lines, it's easy to feel like we are seeing the universe directly. But in reality, what we are seeing is the final step in a long chain of interpretation. Webb does not capture images in the way a traditional camera does. It detects infrared radiation, light that is invisible to the human eye, and records it as raw data. That data is then processed, calibrated, filtered, and mapped into visual formats. Colors are assigned not because they are true in a literal sense, but because they help us distinguish wavelengths, temperatures, and compositions. Structures are enhanced to reveal detail. Noise is reduced to clarify signals. All of this is essential. Without it, the data would remain abstract, almost unreadable. And the mainstream scientific view is very clear on this. These processes are carefully designed, rigorously tested, and widely understood within the field. There is no suggestion that the images are misleading. They are representations, accurate ones, of real data. But even within that clarity, there is a subtle philosophical layer that begins to emerge. Because once data is translated into an image, it becomes something we interpret visually. We look at a galaxy and perceive shape, brightness, symmetry, or irregularity. We see patterns, we categorize, we compare. And in doing so, we rely not just on the data itself, but on the frameworks we use to understand what those patterns mean. For example, When Webb reveals a distant galaxy with a spiral-like structure, we recognize it because we are familiar with spiral galaxies in the nearby universe. When we see a bright, compact object, we may interpret it as a dense cluster of stars. These interpretations are grounded in decades of observation and theory, but they are still, in a sense, interpretations layered on top of processed data. And this becomes particularly important when Webb looks at objects at extreme distances, objects whose light has traveled for over 13 billion years to reach us. At that scale, we are dealing with signals that are faint, stretched, and often incomplete. We are reconstructing a picture of something that existed in a very different cosmic environment, under conditions we are still trying to fully understand, so we can ask, again in a calm and grounded way, how much of what we see is shaped by the assumptions we bring into the process, not in a way that undermines the science, but in a way that highlights the complexity of interpreting something so far removed from direct experience. Another layer to this is the role of algorithms and modeling. When Webb collects spectral data from a distant galaxy, scientists use models to estimate its properties, its mass, its age, its chemical composition. These models are based on known physics, laboratory measurements, and observations of closer objects. They are incredibly sophisticated, but they also involve choices, parameters, assumptions about how certain processes behave under different conditions. For instance, estimating the age of a galaxy often depends on analyzing the light from its stars. Certain wavelengths suggest younger stars, others older ones. But when dealing with galaxies at the very edge of observability, those signals can overlap, blur, or behave in ways that are not entirely straightforward. So models are used to interpret the data, to fit it into a coherent picture. And most of the time, this works remarkably well. But when Webb shows us galaxies that appear unusually bright or unexpectedly structured for their estimated age, it raises a quiet question about whether those models are capturing the full picture. Not that they are wrong, but that they might be incomplete, especially under the extreme conditions of the early universe. This brings us to an interesting point that often goes unnoticed. Science is not just about collecting data. It is about building interpretations of that data that are consistent, predictive, and testable. And when new data arrives that doesn't fit perfectly, the interpretation becomes the focus. So with Webb, we are not just observing distant galaxies. We are testing the limits of the models we use to describe them. And this is where a subtle kind of tension can appear, not a conflict, but a kind of creative pressure. On one side, we have a well-established framework that has explained a vast range of observations. On the other, we have new data that introduces small but persistent questions. And in between, there is a space for careful, grounded speculation. For example, some researchers have begun exploring whether the early universe may have experienced periods of accelerated structure formation, phases where conditions allowed matter to clump together more rapidly than expected. Others are examining whether our assumptions about the initial distribution of matter, how smooth or uneven it was, might need adjustment. There are also discussions about alternative forms of dark matter, or variations in how it interacts with ordinary matter in the earliest epochs. None of these ideas are claims. They are questions, hypotheses, possibilities being explored within the scientific process. But they do point to something larger, because if Webb continues to show us patterns that don't quite align with expectations, the response will not be immediate conclusions. It will be a gradual process of re-examination. Models will be adjusted. Simulations will be refined. New observations will be compared against old ones. Over time, a clearer picture will emerge. And this process is not a sign of uncertainty in a negative sense. It is a sign that we are at the edge of what we currently understand. There's also something quietly humbling about this, because for all our technological advancement, for all the precision of instruments like Webb, we are still interpreting signals from a universe that operates on scales and timescales far beyond human intuition. We are piecing together a story from fragments of light, photons that have traveled across billions of years, carrying with them information that we are only now beginning to decode. And in that sense, Webb is not just a telescope. It is a kind of bridge, connecting us to a past that is almost unimaginably distant, and challenging us to interpret that past with tools that are still evolving. So as we continue, it's worth holding on to a simple but powerful idea. What we are seeing is real, the data is real, the observations are real, but the meaning we assign to those observations, that is something we are still refining. And sometimes, the most interesting discoveries don't come from what is clearly understood, but from the small gaps where understanding is still taking shape. The places where we pause and ask quietly, are we seeing something new, or are we seeing something familiar, in a way we haven't fully recognized yet? As we continue to follow this thread, it becomes almost impossible to avoid one of the most quietly significant aspects of what the James Webb Space Telescope is doing. Not just observing distant galaxies, but detecting the chemical fingerprints of the universe itself. Because beyond structure, beyond brightness, beyond shape, Webb is analyzing light in a way that allows us to infer what these distant objects are actually made of. And this is where the story becomes both more precise and more complex. When Webb observes a distant galaxy or an exoplanet, it doesn't just capture light, it breaks that light apart into a spectrum. Within that spectrum are absorption lines, tiny signatures that correspond to specific elements and molecules. Hydrogen, helium, oxygen, carbon, methane, water vapor. Each leaves a distinct mark. By studying these patterns, scientists can reconstruct the composition of objects that are unimaginably far away. The mainstream explanation of this process is one of the great successes of modern astrophysics. Spectroscopy has been used for over a century, refined through laboratory experiments and observational data. It allows us to determine, with remarkable accuracy, what distant stars and galaxies are made of. And Webb, with its sensitivity to infrared wavelengths, extends this capability further than ever before. But once again, as we look closer, the interesting part is not just what confirms our expectations, but where subtle questions begin to appear. Because one of the key assumptions in cosmology is that the early universe was chemically simple. After the Big Bang, the universe was composed primarily of hydrogen and helium, with only trace amounts of lithium. Heavier elements, what astronomers call metals, were formed later, inside stars, through nuclear fusion and supernova explosions. This process takes time. Stars must form, live, and die, enriching the surrounding space with heavier elements that then become part of new generations of stars and planets. So when we look far back in time, we expect to see objects that are relatively low in these heavier elements. Young galaxies, early stars, chemically primitive environments. And yet, some of Webb's observations suggest that certain distant galaxies may contain more complex chemical signatures than expected for their age. Not dramatically so, but enough to raise a quiet question about how quickly chemical enrichment could have occurred in the early universe. The mainstream interpretation, again, remains grounded. It is possible that early stars were more massive and lived shorter lives, accelerating the production of heavier elements. These so-called population 3 stars, hypothetical first-generation stars, may have burned brightly and briefly, seeding the universe with metals sooner than we had previously modeled. There is ongoing research into whether Webb may have already detected indirect evidence of these early stellar populations. Another possibility is that we are observing particularly active regions, areas where star formation and stellar evolution occurred at an unusually rapid pace. In a universe as vast as ours, variation is expected. Not every region evolves at the same rate, but as we step back and look at the pattern, a subtle question begins to form. If chemical complexity is appearing earlier than expected, what does that say about the overall pace of cosmic evolution? Not just in isolated regions, but across the universe as a whole. Because chemistry is, in many ways, a record of time. The more generations of stars that have lived and died, the richer the chemical environment becomes. So when we detect heavier elements in distant galaxies, we are not just seeing what they are made of, we are seeing evidence of processes that must have already taken place. And if those processes occurred faster than expected, it suggests that the early universe may have been more dynamic, more active than our models currently assume. There is also another layer to consider, one that moves slightly beyond galaxies and into the study of exoplanets. Webb has already begun analyzing the atmospheres of planets orbiting distant stars, detecting molecules like water vapor, carbon dioxide, and methane. These observations are still in their early stages, and interpretations are cautious. But they represent a significant step forward in our ability to study the conditions of worlds beyond our solar system. And here, once again, interpretation becomes key. Because detecting a molecule in an atmosphere does not immediately tell us its origin. Methane, for example, can be produced through biological processes, but also through geological ones. Water vapor can exist in a wide range of environments, not all of them conducive to life as we know it. So while these detections are exciting, they are also ambiguous. And ambiguity in science is not a flaw. It is an invitation to look closer. So we find ourselves in a familiar position. Webb provides us with unprecedented data, but that data opens up new questions about how to interpret what we are seeing. Not just in terms of individual discoveries, but in terms of the broader patterns that begin to emerge. Are we observing a universe that evolved more quickly than expected? Are there processes in the early universe that we have not yet fully accounted for? Are our models of chemical evolution complete? Or are they approximations that will need to be refined as more data becomes available? And perhaps most interestingly, how do we distinguish between what is truly unexpected and what simply appears unexpected because of the limits of our current understanding? Because it's entirely possible that everything Webb is showing us does fit within the framework of known physics, once that framework is expanded just enough to accommodate the new data. But it's also possible that, as we gather more observations, small inconsistencies will begin to connect, forming patterns that point toward deeper adjustments in how we think about the universe. Not revolutions, not sudden paradigm shifts, but gradual, careful changes, the kind that happen when evidence accumulates over time. And all of this is happening in a very quiet way. There are no dramatic announcements that everything we know is wrong. There are no definitive claims that rewrite cosmology overnight. Instead, there is a steady flow of data, a series of observations that, piece by piece, are refining our understanding. And Webb continues to operate, far from Earth, positioned at a point where gravitational forces balance just enough to keep it stable, constantly collecting light from the deepest parts of the cosmos. Light that carries with it not just images, but chemical signatures, timelines, clues about processes that unfolded billions of years ago. And as we interpret those clues, carefully and methodically, we are left with a simple but profound realization. We are not just observing the universe, we are learning how to read it. And sometimes, as we learn to read more clearly, we begin to notice details that were always there, but never fully understood. So the question becomes, as Webb continues to refine that picture, what else might emerge from the data that quietly challenges us to look again? As we move further into this quiet examination, it becomes important to look not just at what the James Webb Space Telescope is observing in terms of distant galaxies and chemical signatures, but at something even more foundational to how we interpret all of it: the concept of light itself and how it travels across the universe. Because everything Webb shows us, every galaxy, every faint structure, every spectral signature, is carried to us by light that has been moving through space for billions of years. And the assumptions we make about that journey shape everything we believe we are seeing. In mainstream physics, the behavior of light across cosmic distances is well described by the framework of general relativity, first proposed by Albert Einstein. According to this framework, space itself is not static. It expands. And as it expands, the light traveling through it is stretched, increasing its wavelength. This is what we refer to as redshift. The greater the redshift, the further away, and therefore the further back in time, an object is believed to be. This relationship between redshift and distance is one of the cornerstones of modern cosmology. It allows us to construct a timeline of the universe, placing galaxies and structures at different stages of cosmic history. And Webb, with its ability to detect highly redshifted infrared light, extends this timeline deeper than ever before. But as we've been noticing throughout this exploration, the interesting questions tend to arise not from the principle itself, but from how precisely it applies at the extremes. Because when we are observing objects at redshift levels corresponding to over 13 billion years ago, we are operating at the very edge of our observational capabilities. The signals are faint, the uncertainties are larger, and small variations in interpretation can have significant effects on how we place those objects within the cosmic timeline. The mainstream view is clear and consistent. Redshift is a reliable indicator of distance, supported by multiple independent observations, including the expansion of the universe and the cosmic microwave background. There is no widely accepted alternative that explains the data more effectively. But even within that framework, there are subtle areas of ongoing investigation. For instance, the exact rate at which the universe is expanding, known as the Hubble constant, has been the subject of increasing attention. Measurements based on observations of nearby galaxies sometimes yield slightly different values than those based on observations of the early universe. This discrepancy is small, but persistent. It's often referred to as the Hubble tension. Now, Webb is not the sole instrument involved in this discussion, but its observations contribute to the broader data set that scientists use to refine these measurements. And if the rate of expansion is not perfectly understood, even by a small margin, it could influence how we interpret redshift and therefore how we place distant objects in time. Again, this is not about overturning established science. It's about recognizing that even well-supported models can contain areas of uncertainty, especially when pushed to their limits. There's also the question of what happens to light over such immense distances. In theory, light travels through the vacuum of space largely unaffected, aside from gravitational influences and cosmic expansion. But when that journey spans billions of years, passing through regions of varying density, interacting with intergalactic gas, and potentially influenced by large-scale structures, it becomes a remarkably complex path. Webb's observations of gravitational lensing, where massive objects bend light, magnifying distant galaxies, highlight just how dynamic that journey can be. Light doesn't always travel in straight lines across the cosmos. It curves, stretches, and sometimes takes paths that allow us to see objects that would otherwise be hidden. And this introduces an interesting layer to our interpretation. Because when we observe a distant galaxy through gravitational lensing, we are not just seeing it directly. We are seeing it as its light has been altered by massive objects along the way. The mainstream approach accounts for this, using models to reconstruct the original image. But once again, interpretation plays a role. So we can ask, calmly and carefully, how much of what we observe is influenced by the path that light has taken? And how precisely can we reconstruct that path? Not as a challenge to the science, but as an acknowledgement of the complexity involved. Another subtle point to consider is time itself. When we say that we are looking 13 billion years into the past, we are describing time as measured within our current understanding of cosmic expansion. But time, in the context of general relativity, is not absolute. It is influenced by gravity, motion, and the structure of space itself. This doesn't mean that our measurements are unreliable, but it does mean that time at cosmic scales is not as straightforward as it might seem. It is deeply intertwined with the very fabric of the universe. So when Webb shows us a galaxy that appears unexpectedly mature for its estimated age, part of the question becomes not just how that galaxy formed, but how precisely we are defining its place in time. And this brings us back to a recurring theme. We are observing real data. We are applying well-established models. But those models are being tested at scales that push them to their limits. And at those limits, small uncertainties become more noticeable. There is also something quietly profound about the idea that every photon Webb detects has been traveling for billions of years, uninterrupted, carrying with it information about a moment in the distant past. That light began its journey long before our planet formed, before our solar system existed, before even our galaxy had taken its current shape. And now, after all that time, it arrives at a telescope positioned far beyond Earth, where it is captured, analyzed, and interpreted by a species that has only recently developed the ability to ask these kinds of questions. There's a kind of symmetry in that, a quiet connection between observation and existence. But from a purely analytical perspective, it also reminds us of something important. We are working with signals that have traveled immense distances under conditions we are still striving to fully understand. And while our models are incredibly powerful, they are, by necessity, approximations of a reality that is far more complex than any single framework can fully capture. So as Webb continues to gather light from the edge of the observable universe, it is not just filling in details, it is refining the very way we think about distance, time, and the journey of light itself. And perhaps, as more data accumulates, the questions surrounding redshift, expansion, and cosmic timelines will become clearer, or perhaps they will become more nuanced. Because sometimes, the deeper we look, the more we realize that understanding the universe is not just about seeing further. It's about learning how to interpret what further actually means. And in that sense, Webb is not just extending our vision, it is quietly reshaping our perspective. So the question lingers. If even the journey of light, something we consider so fundamental, contains layers of complexity we are still exploring, what else, in our understanding of the universe, might be just as dependent on how we choose to interpret it? As we continue drifting deeper into this quiet examination, there's another layer of the James Webb Space Telescope story that begins to emerge. One that doesn't immediately stand out in the images, but sits just beneath them. The idea of resolution, and what it really means to see clearly at cosmic scales. Because Webb is often described as giving us the sharpest, most detailed view of the distant universe ever achieved. And in many ways, that is absolutely true. But clarity, especially at these distances, is not as simple as it first appears. When we look at Webb's deep field images, those dense, almost overwhelming views filled with countless galaxies, it's easy to feel as though we are observing these objects in extraordinary detail. and compared to previous instruments like the Hubble Space Telescope, we are. Webb's mirror is larger, its instruments are more sensitive, and its infrared capabilities allow it to peer through dust and detect faint, distant light that would otherwise remain invisible. But even with all of that, the galaxies we are observing at the edge of the observable universe are still incredibly small in angular size. They occupy only a tiny fraction of the telescope's field of view. What we see as a structured object, a disk, a cluster, a bright core, is often just a handful of pixels, carefully processed and enhanced. And this is where an interesting question begins to take shape. Because when we interpret the structure of these distant galaxies, when we describe them as mature or disk-like or unexpectedly organized, we are doing so based on limited visual information. The data is real, the observations are valid, but the level of detail is still constrained by distance. The mainstream scientific approach accounts for this. Astronomers use statistical methods, simulations, and comparisons with closer galaxies to interpret what these distant shapes likely represent. They consider how light spreads across the detector, how noise might influence the image, how gravitational lensing might distort the appearance. These are careful, methodical processes designed to extract as much reliable information as possible. But even with those methods, interpretation remains a key part of the process. So we can ask, gently and without skepticism, how confident can we be in the fine details of objects that are so far away that their entire structure fits within just a few pixels? Not in a way that dismisses the observations, but in a way that acknowledges the limits of resolution. Because resolution is not just about how sharp an image looks, it's about how much information is actually contained within that image. And at extreme distances, even the most advanced telescope is working with very limited signals. This becomes particularly relevant when we consider some of the claims about early galaxy structure. When Webb detects a galaxy that appears to have a defined shape, a possible disk, or a concentrated core, it suggests a level of organization that, according to current models, should take time to develop. But if that structure is inferred from a small number of pixels, processed through complex algorithms, it introduces a layer of uncertainty, not enough to invalidate the observation, but enough to encourage careful interpretation. And this is exactly what the scientific community is doing. Papers are being published, debated, refined. Some researchers argue that these early galaxies are indeed more structured than expected. Others suggest that what we are seeing may be influenced by resolution limits, noise, or the way light is distributed across the detector. This is not disagreement in the sense of conflict. It is the normal process of refining understanding. But it does highlight something important. Because when Webb reveals something that appears to challenge expectations, the question is not just, what are we seeing, but also, how are we seeing it? And that question becomes even more interesting when we consider how much of modern astronomy relies on indirect observation. We are not traveling to these galaxies. We are not observing them from multiple angles. We are receiving a stream of photons, limited, distant, ancient, and reconstructing a picture from that stream. It's an extraordinary achievement, but it is also an inherently interpretive process. There's also another layer to resolution that is less obvious, but just as important. Webb's ability to see deeper into space means it is also looking through more intervening material, gas, dust, and other cosmic structures that lie between us and the objects we are observing. While infrared light can pass through much of this material, it is not entirely unaffected. Subtle distortions, scattering, or absorption can influence the signal. Again, these effects are well understood and accounted for in data processing. But when dealing with extremely faint, distant objects, even small influences can become significant. So as Webb pushes the boundaries of observation, it is also pushing the limits of how precisely we can interpret what we see. And this brings us back to a recurring theme in this exploration. We are not just expanding our view of the universe, we are expanding the complexity of how we understand that view. Because clarity, at this scale, is not absolute. It is layered. It depends on instrumentation, processing, modeling, and interpretation, all working together to produce a coherent picture. And sometimes, when new data introduces unexpected patterns, it's not immediately clear whether those patterns reflect something fundamentally new, or something that emerges from the way we are observing and interpreting the data. This doesn't diminish the significance of Webb's discoveries. If anything, it enhances them, because it reminds us that every image, every observation, every data point exists within a framework of understanding that is itself evolving. And as that framework evolves, so too does our interpretation of what Webb is showing us. So when we see a distant galaxy that appears more complex than expected, we can hold two ideas at once. One, that it may indeed represent something new about how galaxies form and evolve. And two, that our interpretation of its structure may be influenced by the limits of resolution and the processes we use to reconstruct the image. Neither idea cancels the other out. They exist together in that quiet space where observation meets understanding. And it is within that space that science moves forward, not by choosing one explanation immediately, but by examining both, carefully, over time. So as Webb continues to deliver deeper and more detailed views of the cosmos, it also invites us to refine not just what we see, but how we see it. And perhaps, as resolution improves, as more data is gathered, as interpretations are tested and retested, some of these questions will settle into clearer answers. Or perhaps they will lead to new ones. Because when you are looking at the universe at its most distant edges, clarity is not just about sharpness. It's about understanding the limits of what can be known and recognizing that those limits are always, quietly, shifting. So the question remains, when we say we are seeing the universe more clearly than ever before, are we seeing more detail? Or are we beginning to see the complexity of interpretation itself? As we continue this gradual unfolding, there is another aspect of the James Webb Space Telescope that begins to feel almost paradoxical the longer you sit with it. And that is the idea that, while Webb is designed to look farther than ever before, it is also revealing just how dependent our understanding of the universe is on invisible components. Not things that are hidden in the sense of being undiscovered, but things that are deeply embedded in our models, shaping our interpretations, even though we cannot observe them directly. At the center of this is something we've touched on briefly before, the concept of dark matter. According to mainstream cosmology, dark matter makes up a significant portion of the total mass of the universe. It does not emit light, does not absorb light, and does not interact with electromagnetic forces in any way we can directly detect. And yet, its presence is inferred from the gravitational behavior of galaxies, galaxy clusters, and large-scale cosmic structures. Without dark matter, many of the observations we have simply wouldn't make sense. Galaxies rotate too quickly for the visible matter alone to hold them together. Light bends around massive structures in ways that suggest more mass than we can see. The large-scale distribution of galaxies across the universe appears to follow patterns that are best explained by an underlying framework of unseen mass. So dark matter, in the standard model, is not optional, it is essential. And Webb, interestingly, does not directly detect dark matter, but it observes the effects that are attributed to it. When Webb captures images of gravitational lensing, where massive galaxy clusters bend and magnify the light from objects behind them, it is effectively mapping the distribution of mass, both visible and invisible. The patterns of distortion allow scientists to infer where dark matter must be based on how strongly light is bent. This is well-established science. These methods have been refined over decades, and they consistently produce results that align with the presence of dark matter. But as Webb extends these observations deeper into the universe, into earlier epochs, a subtle question begins to form. Because if we are observing galaxies that appear more massive or more developed than expected at early times, then the role of dark matter in shaping those galaxies becomes even more important. In the standard view, dark matter acts as a kind of scaffolding. It forms halos that provide the gravitational framework for ordinary matter to collapse into galaxies. The distribution and behavior of dark matter influence how quickly structures can form, how they evolve, and how they interact. So if galaxies are forming earlier or more efficiently than expected, it naturally leads to a question about whether our understanding of that scaffolding is complete. Not whether dark matter exists, but whether we fully understand how it behaves under the extreme conditions of the early universe. And this is where things become quietly intriguing, because dark matter, as a concept, is based on inference. We observe its effects, but we have not directly detected the particles that would make it up. There are many candidates, weakly interacting massive particles, axions and others, but none have been confirmed. So our models of dark matter are built on a combination of observation and theoretical physics, grounded, but still incomplete. And when Webb provides new data that interacts with those models, it doesn't challenge the existence of dark matter, but it does invite a closer look at its properties. Could dark matter have behaved differently in the early universe? Could it have interacted more strongly or clustered more efficiently than we currently assume? Are there variations in its distribution that we have not yet accounted for? These are active areas of research, not fringe ideas, but questions being explored within the scientific community. There is also another, slightly more subtle angle to consider. Because while dark matter explains many observations very well, it is not the only framework that has been proposed. There are alternative theories that attempt to modify our understanding of gravity itself, rather than introducing unseen matter. These theories, such as modifications to Newtonian dynamics, are less widely accepted, largely because they struggle to explain the full range of cosmological observations as effectively as dark matter does. But they exist as part of the broader conversation. And Webb's observations, by providing more detailed data on galaxy formation and structure, contribute to that conversation, not by proving one model over another, but by adding new constraints, new pieces of evidence that any successful theory must account for. So we find ourselves once again in that familiar space between observation and interpretation. Webb shows us galaxies, structures, gravitational effects. We interpret those observations through models that include dark matter as a central component. And when something doesn't align perfectly, we refine those models or explore alternative possibilities, all within the framework of careful, evidence-based science. But there is something quietly profound about the idea that so much of our understanding of the universe depends on something we cannot directly see. It's not a flaw in the science, it's a reflection of how science works. We infer the existence of things based on their effects. We build models that explain those effects. We test those models against new data, and over time, those models become more precise, or they evolve into something new. Webb, in this sense, is not just observing the visible universe. It is mapping the invisible. Every instance of gravitational lensing, every measurement of galaxy rotation, every inference about mass distribution, contributes to a picture of a universe that is shaped as much by what we cannot see as by what we can. And as Webb looks further back in time, it is effectively asking a quiet question of that invisible framework. Was it always the same? Did dark matter behave in the early universe exactly as it does now? Or are there nuances we have yet to uncover? Because if the scaffolding itself is even slightly different from what we assume, it could influence everything built upon it. Galaxy formation, structure, evolution, all of it. And yet, the tone of this exploration remains the same. We are not here to replace one idea with another. We are here to observe, to compare, to notice where data and expectation align and where they begin to drift apart. Because it is in those small drifts, those subtle inconsistencies, that the most meaningful refinements often begin. So as Webb continues its quiet work, collecting light, mapping structures, revealing patterns, it is also, in a way, illuminating the parts of our understanding that are still just out of reach, not hidden, not unknowable, but not yet fully defined. And perhaps that is what makes this moment in science so uniquely interesting. We are not just exploring the universe, we are exploring the limits of the models we use to describe it. And sometimes, the most important discoveries are not the ones that confirm what we know, but the ones that gently remind us how much more there is to understand. As we continue this slow, careful exploration, there is another layer of the James Webb Space Telescope that begins to reveal itself. Not in what it directly shows us, but in how it reshapes the questions we ask about origins. Because at the deepest level, Webb is not just observing galaxies or stars. It is observing the earlier stages of structure in the universe. And whenever we begin to approach the concept of the beginning, even in a scientific sense, the clarity of our models often gives way to something more open-ended. In the standard cosmological framework, everything traces back to the Big Bang, not as an explosion in space, but as an expansion of space itself. From that initial state, the universe cools, particles form, atoms emerge, and eventually, under the influence of gravity, structure begins to appear. Over time, small fluctuations in density grow into stars, galaxies, and the vast cosmic web. This narrative is supported by strong evidence. The cosmic microwave background provides a snapshot of the universe roughly 380,000 years after the Big Bang. The distribution of galaxies aligns with predictions from simulations. The relative abundance of light elements matches theoretical calculations. It is a coherent and well-supported picture. But Webb is now pushing our observational reach closer to that early period than ever before. And as it does, it begins to probe a part of the timeline where our models are less constrained by direct observation and more reliant on extrapolation. Because even with Webb, we are not seeing the very beginning. We are seeing light from hundreds of millions of years after the Big Bang, a period often referred to as the cosmic dawn, when the first stars and galaxies began to illuminate the universe. Before that, there is darkness, not in a metaphorical sense, but in a literal one. A period where the universe had cooled enough for atoms to form, but before stars had ignited. This era, sometimes called the Dark Ages, remains largely unobserved. We infer its properties based on models and indirect evidence, but we do not yet have direct images or detailed data from that time. So Webb, in a way, is approaching the edge of what we can directly observe. And as it does, it begins to highlight the transition between what we know through observation and what we infer through theory. This transition is subtle, but important, because when Webb detects galaxies at extremely high redshifts, objects that existed very early in the universe, it is effectively narrowing the gap between observation and origin. It is showing us what the universe looked like closer and closer to that initial state. And when those observations introduce unexpected patterns, galaxies forming earlier, structures appearing more complex, it raises a quiet question about how smooth that transition really is. Does the universe evolve in a steady, predictable way, from simplicity to complexity? Or are there phases, periods of rapid change, bursts of activity, or conditions that accelerate structure formation that we have not yet fully accounted for? The mainstream approach remains cautious. Scientists are actively refining models of early star formation, exploring how the first stars may have influenced their surroundings, and examining how radiation, gravity, and matter interacted during those early epochs. There is ongoing work to understand the process of reionization, the period when the first luminous objects ionize the surrounding hydrogen, making the universe transparent to light once again. These are complex, well-studied areas of cosmology, but Webb's data is beginning to add new layers to that complexity. Because if the earliest galaxies are more numerous, more massive, or more structured than expected, it suggests that the transition from the Dark Ages to the cosmic dawn may not have been as gradual as we thought. And this leads to a broader, more philosophical question, one that remains grounded, but open. How much of our understanding of the early universe is shaped by the limits of what we can currently observe? Because until now, much of our knowledge about these earliest periods has come from indirect evidence, background radiation, simulations, theoretical models. Webb is now providing direct observations that can confirm, refine, or challenge those ideas. And when direct observation meets theoretical expectation, the comparison becomes incredibly valuable. Sometimes it confirms what we already believe. Sometimes it reveals small discrepancies, and occasionally it opens the door to entirely new lines of inquiry. There is also something else worth considering here. Because when we talk about the beginning of the universe, we are using a concept that is, in some ways, limited by our own perspective. Time, as we experience it, flows in one direction. Causes precede effects. Events unfold in sequence. But at the scale of the universe, especially near its earliest moments, time itself may not behave in ways that are fully intuitive. The equations of physics allow for scenarios where time behaves differently under extreme conditions. Quantum effects, gravitational curvature, and the nature of space-time itself all come into play. This doesn't mean that our current models are wrong, but it does mean that the closer we get to the origin, the more those models are stretched to their limits. And Webb, by extending our observational reach, is bringing us closer to that boundary. Not crossing it, but approaching it. And as we approach it, the questions naturally become more fundamental. Not just about how galaxies form, but about how the universe itself evolves from its earliest state. There is no need to jump to conclusions here. The scientific process is ongoing. Data is being analyzed, models are being updated, new observations are being planned. Webb is just one instrument, an incredibly powerful one, but part of a larger effort to understand the universe. But there is something quietly significant about this moment, because for the first time, we are not just theorizing about the earliest structures in the universe, we are beginning to see them. And what we are seeing, while broadly consistent with our expectations, carries just enough nuance, just enough variation to remind us that our understanding is still evolving. So as we continue this journey, it's worth holding on to that sense of balance. We are grounded in evidence, we are guided by models, but we are also open to refinement, to adjustment, to the possibility that the universe may be slightly more complex, slightly more dynamic than our current frameworks fully capture. And in that space, between what is known and what is still being understood, Webb continues to operate, quietly collecting light from the edge of time itself. Light that may, piece by piece, bring us closer to answering one of the most enduring questions we can ask. Not just what the universe looks like, but how it became what it is. As we continue to settle deeper into this exploration, there is another dimension of the James Webb Space Telescope that becomes increasingly difficult to ignore. And that is not just what it reveals about the universe itself, but what it reveals about the limits of prediction. Because long before Webb ever launched, scientists had already built detailed models of what they expected it to find. Simulations of galaxy formation, predictions about the number and brightness of early galaxies, estimates of chemical composition, all of it grounded in decades of observation and theory. And in many ways, those predictions were remarkably accurate. Webb has confirmed a vast number of expectations. It has observed galaxies at extreme distances, detected atmospheric signatures on exoplanets, and revealed structures that align with our broader understanding of cosmic evolution. The foundation holds, but as we've been tracing throughout this journey, the most interesting moments are not where prediction and observation align perfectly. They are where they almost align. Because Webb has introduced a subtle but persistent theme into modern cosmology, that our predictions, while strong, may not be as precise as we once believed when pushed to the very edges of the observable universe. Take, for example, the predicted number of early galaxies. Before Webb, models suggested a certain distribution, how many galaxies we should expect to see at different stages of the universe's early timeline. These predictions were based on simulations that incorporate dark matter, gas dynamics, star formation, and feedback processes from stars and black holes. When Webb began its deep field observations, it found galaxies, plenty of them, but in some cases, more than expected. Not in a way that invalidates the models entirely, but enough to prompt a closer look. Some regions appear to contain a higher density of bright, early galaxies than simulations had predicted. This has led to discussions about whether star formation in the early universe was more efficient, or whether our models underestimate how quickly matter could organize into luminous structures. The mainstream response is measured, as always. Simulations are being updated, parameters are being adjusted. Researchers are exploring whether certain assumptions, such as the efficiency of gas cooling or the impact of early stellar radiation, need to be refined. And this is exactly how science progresses. But there is something quietly revealing about this process, because it highlights the difference between predicting a system and observing it directly. Simulations, no matter how advanced, are built on assumptions. They incorporate known physics, but they must simplify certain aspects of reality to remain computationally feasible. They approximate processes that may, in reality, be far more complex. So when Webb provides direct observational data, it acts as a kind of calibration point. And sometimes, that calibration reveals that the system behaves just a little differently than expected. There is also another layer to this. Because prediction in cosmology is not just about individual objects, it's about patterns. The large-scale structure of the universe, the distribution of galaxies, the rate at which stars form over time. These are all patterns that emerge from the underlying physics. And Webb, by extending our view deeper into space and further back in time, is giving us access to earlier parts of those patterns. It's like seeing the opening chapters of a story we've mostly understood from the middle onward. And when you finally read those opening chapters, you sometimes find that they are not exactly what you imagined, not completely different, but nuanced in ways that change how you interpret everything that follows. So we can ask, again in that calm, grounded way, if our predictions about the early universe are slightly off, what does that imply about the processes that shaped everything we see today? Because the early universe is not just a distant curiosity, it is the foundation upon which all later structure is built. Galaxies evolve, merge, and grow over time, but their initial conditions matter. And if those initial conditions were different from what we've modeled, even subtly, it could influence how we understand the entire timeline of cosmic evolution. There is also the question of feedback, how early stars and galaxies influence their surroundings. In current models, intense radiation from young stars can heat surrounding gas, slowing down further star formation. Supernova explosions can push material outward, regulating the growth of galaxies. These feedback processes are essential to preventing galaxies from forming too quickly or becoming too massive too early. But if Webb is showing us galaxies that seem to have grown rapidly despite these feedback mechanisms, it raises a question about whether those processes behaved differently in the early universe. Were they less effective? Were there conditions that allowed galaxies to bypass or overcome these limitations? Or are we observing particularly unusual regions that don't represent the average behavior of the universe? These are the kinds of questions that are now being explored, not as radical departures from established science, but as refinements. And perhaps that is the key theme that continues to emerge. Webb is not rewriting the story of the universe. It is adding detail to it. But sometimes, adding detail reveals that the outline we were working with was just slightly incomplete. And there is something deeply human about that, because it mirrors the way we come to understand anything complex. We start with broad ideas, patterns that make sense, models that explain most of what we see. And then, as we look closer, we begin to notice exceptions, variations, details that require us to adjust our understanding, not to abandon it, but to deepen it. And Webb, in its quiet, methodical way, is doing exactly that for our understanding of the cosmos. It is showing us that even at the largest scales, even with the most refined models, there is still room for surprise. Not dramatic, disruptive surprise, but subtle, thoughtful surprise. The kind that invites us to look again, to refine our assumptions, to ask better questions. So as we continue, it becomes less about whether Webb will confirm or challenge our models, and more about how it will shape them. Because every new observation, every unexpected pattern, every small inconsistency becomes part of a larger process, a process that is still unfolding. And perhaps, as more data is gathered, as predictions are tested and refined, we will begin to see those patterns more clearly. Or perhaps, we will discover that the universe is just a little more complex, a little more dynamic than even our best models can fully capture. And if that's the case, then Webb is not just observing the universe, it is teaching us how to understand it, one refinement at a time. As we continue to move deeper into this quiet analysis, there is another aspect of the James Webb Space Telescope that begins to feel almost understated. Yet, it may be one of the most significant of all. Not because it challenges our understanding directly, but because it expands the range of what can even be asked. And that aspect is Webb's ability to study not just distant galaxies, but the atmospheres of worlds orbiting other stars, exoplanets that exist far beyond our solar system. At first, this might seem like a separate topic entirely. Galaxies, cosmic timelines, early universe structure, and then suddenly, planets. But the connection is deeper than it appears. Because when we begin to analyze the atmospheres of distant planets, we are no longer just asking how the universe formed. We are asking what conditions exist within it, across space and time. Webb's instruments allow it to perform transmission spectroscopy, observing starlight as it passes through the atmosphere of a planet during a transit. As that light filters through the gases surrounding the planet, certain wavelengths are absorbed, leaving behind a spectral fingerprint. From that fingerprint, scientists can infer the presence of molecules such as water vapor, carbon dioxide, methane, and others. This is an extraordinary capability. It allows us to study the composition of worlds that we cannot see directly, worlds that are, in many cases, hundreds or thousands of light years away. The mainstream interpretation of these observations is careful and precise. When a molecule is detected, it is reported with statistical confidence levels, uncertainties, and alternative explanations. There is no rush to declare discoveries beyond what the data supports. And yet, even within that careful framework, something interesting begins to emerge. Because the detection of certain molecules, particularly combinations of them, can raise questions about the processes occurring on those planets. For example, methane and carbon dioxide can both be produced through non-biological processes. But on Earth, their simultaneous presence in certain proportions is associated with biological activity. This does not mean that detecting these molecules elsewhere indicates life. Far from it. The mainstream view emphasizes that there are many ways to produce these gases without biology. But it does mean that, for the first time, we are approaching a point where we can begin to ask more detailed questions about planetary environments. And this is where the tone of the conversation shifts slightly, not into speculation without grounding, but into a broader awareness of what Webb is enabling. Because until recently, the idea of analyzing the atmosphere of a distant planet was largely theoretical. Now, it is becoming observational, and with observation comes interpretation. Just as with galaxies, just as with chemical signatures, the data Webb provides is real, but the meaning we assign to it depends on models, assumptions, and context. For instance, when Webb detects water vapor in an exoplanet's atmosphere, the immediate interpretation might be that the planet has a significant amount of water, but the form that water takes, vapor, clouds, oceans, depends on temperature, pressure, and a range of environmental factors that we cannot directly observe. Similarly, methane might suggest certain chemical processes, but without knowing the full context of the planet's geology, radiation environment, and atmospheric dynamics, it remains an open question. So once again, we find ourselves in that familiar space between observation and understanding. But there is something unique about this particular area, because when we study distant galaxies, we are looking at the past, billions of years ago. But when we study exoplanets, we are often looking at systems that exist in a more contemporary sense. Systems that may still be evolving, still changing. And that introduces a different kind of question. Not just how the universe formed, but what it is doing now. There is also a subtle connection here to the broader themes we've been exploring. Because the chemical composition of planets, the formation of atmospheres, the presence of certain molecules, all of these are influenced by the same processes that govern galaxy formation and evolution. The distribution of elements, the life cycle of stars, the dynamics of cosmic structures. They all feed into the environments that planets emerge from. So when Webb detects complex molecules in a distant atmosphere, it is, in a way, tracing the outcome of processes that began billions of years earlier. And if those processes, star formation, chemical enrichment, galaxy evolution, are more dynamic or occur more rapidly than we've modeled, it could influence how we think about planetary systems as well, not in a direct, immediate way, but as part of a larger pattern. And this brings us back to a quiet but important realization. Webb is not just expanding our view outward, it is connecting different layers of the universe, linking the earliest galaxies to the present-day environments of distant worlds. And as it does, it begins to blur the boundaries between separate areas of study. Cosmology, astrophysics, planetary science, all becoming part of a single, interconnected picture. But with that interconnectedness comes complexity, because each layer, each type of observation, introduces its own uncertainties, its own interpretations, its own questions. And when those layers overlap, the questions become deeper. For example, if the early universe formed structures more quickly than expected, how might that influence the distribution of elements needed for planet formation? If chemical enrichment occurred earlier, could that mean that planetary systems formed sooner or in different environments than we've assumed? And if Webb begins to detect atmospheres with unexpected compositions, how do we distinguish between what is truly unusual and what simply reflects the diversity of planetary systems? These are not questions with immediate answers. They are part of an ongoing process, but they do highlight something important. Because for the first time, we are not just theorizing about distant worlds, we are beginning to analyze them. And that analysis, like everything else Webb provides, exists within a framework of interpretation that is still evolving. So as we continue, it becomes less about individual discoveries and more about the growing network of connections between them. Galaxies, stars, planets, atmospheres, all part of a continuous chain of processes that Webb is helping us observe in greater detail than ever before. And within that chain, small inconsistencies, subtle variations, unexpected patterns begin to matter, because they don't just affect one area of study, they ripple outward, influencing how we understand the entire system. So as Webb continues its quiet work, analyzing light, detecting molecules, revealing distant environments, it is also, in a way, expanding the scope of our questions, not just about where we came from, but about what exists right now across the vastness of space. And perhaps, as more data is gathered, as more atmospheres are analyzed, as more patterns begin to emerge, we will start to see those connections more clearly. Or perhaps, we will realize that the universe is not just more complex than we imagined, but more interconnected in ways we are only beginning to understand. As we continue to move further into this quiet and careful examination, there is another dimension of the James Webb Space Telescope that begins to emerge, not from any single discovery, but from the patterns that form when multiple observations are placed side by side. Because one of the most subtle ways scientific understanding evolves is not through isolated data points, but through the gradual recognition of consistency or inconsistency across many different observations. And Webb, by providing such a large volume of high-quality data in a relatively short time, is beginning to allow those patterns to form more quickly than before. In the past, observations of the early universe were limited. Instruments like the Hubble Space Telescope gave us glimpses, deep fields that revealed thousands of galaxies, snapshots that hinted at structure and evolution. But the data was sparse enough that individual anomalies could be explained away as outliers, unusual, but not necessarily significant. Webb changes that dynamic, because now, instead of a handful of distant observations, we are beginning to accumulate a broader data set, multiple deep fields, multiple galaxy surveys, multiple independent observations of early structures. And when similar patterns begin to appear across these data sets, they become harder to ignore. For example, we've already touched on the idea that some early galaxies appear more massive or more developed than expected. When this was first observed, it could be treated as a single case, interesting, but not necessarily representative. But as more observations come in and similar characteristics appear in multiple galaxies, it begins to look less like an exception and more like a pattern. Not a definitive one, but a developing one. And this is where the scientific process becomes particularly careful, because identifying a pattern is not the same as explaining it. The mainstream approach is to gather more data, test different models, and determine whether the pattern holds under closer scrutiny. Are these galaxies truly more massive, or are we misinterpreting their light? Are they representative of the early universe as a whole, or are they part of a biased sample, regions that are unusually dense or active? These questions are being actively explored, but even before answers are fully formed, the presence of a pattern changes the conversation, because it shifts the focus from "why does this one object look unusual?" to "why do multiple objects share this characteristic?" And that is a much deeper question. There is also another layer to this idea of patterns, one that connects different types of observations, because Webb is not just observing galaxies, it is observing star-forming regions, exoplanet atmospheres, interstellar chemistry, and more. Each of these areas produces its own data, its own patterns, and sometimes those patterns begin to align in unexpected ways. For instance, if Webb is detecting earlier than expected chemical enrichment in galaxies, and also observing complex molecules in certain environments, it raises a question about whether these are independent observations or parts of a larger, interconnected process. Again, the mainstream view treats each observation within its specific context. Galaxy evolution is studied separately from planetary atmospheres, which are studied separately from interstellar chemistry. This separation allows for precise, focused analysis. But Webb, by collecting data across all these domains simultaneously, begins to blur those boundaries. And when boundaries blur, connections become more visible, not necessarily obvious, but possible. So we can ask, quietly and without assumption, are these patterns independent, or are they reflections of a deeper underlying process that we are only beginning to recognize? Because if multiple lines of observation begin to point in similar directions, even subtly, it can suggest that our current models, while accurate in many ways, may be missing a unifying layer. Not something that replaces them, but something that connects them. There is also the question of scale. Patterns observed on small scales, individual galaxies, specific exoplanets, may not immediately translate to the universe as a whole. But if those patterns persist across different regions, different distances, different conditions, they begin to suggest something more general. And Webb, by extending our observational reach, allows us to test whether patterns observed nearby also exist in the distant universe. Sometimes they do, sometimes they don't, and both outcomes are equally informative. Because when a pattern holds across scales, it strengthens our confidence in the underlying model. And when it doesn't, it highlights an area where our understanding may need refinement. There is something almost meditative about this process, not in the sense of relaxation, but in the sense of patience. Science, especially at this scale, does not move quickly. It accumulates evidence. It tests ideas. It refines models over time. And Webb is accelerating that process, not by providing instant answers, but by providing a steady stream of high-quality data that allows patterns to emerge more clearly. But with that clarity comes responsibility, because it becomes easier to see patterns, but also easier to overinterpret them. And this is something the scientific community is deeply aware of. Every potential pattern must be tested against alternative explanations. Selection effects, observational biases, statistical fluctuations, all must be considered. The goal is not to find patterns, but to find patterns that hold under scrutiny. So as we look at Webb's observations, it's important to hold that balance, to recognize that patterns are forming, but that their meaning is still being carefully evaluated. And within that balance, there is a kind of quiet anticipation. Because if these patterns persist, if they continue to appear across different data sets, they may begin to point toward deeper insights about how the universe works, not in a dramatic, disruptive way, but in a way that gradually reshapes our understanding. So as Webb continues its work, collecting data, revealing structures, connecting observations, it is also, in a sense, weaving together a tapestry of information, a tapestry that is still incomplete, but becoming more detailed with each new observation. And as that tapestry becomes clearer, the patterns within it may begin to stand out more distinctly, or perhaps they will reveal that what we thought were patterns were only fragments of something larger, something more complex, that we are only just beginning to perceive. And that is where this journey continues, not toward immediate answers, but toward a deeper awareness of the questions themselves. Because sometimes the most important step in understanding the universe is not finding a single explanation, but learning how to recognize the patterns that guide us toward one. As we continue deeper into this slow unfolding, there is a quieter dimension of the James Webb Space Telescope that begins to emerge, not from any single observation, not even from patterns across data, but from something more subtle: the relationship between confidence and uncertainty in modern science. Because one of the most interesting aspects of Webb's discoveries is not that they contradict what we know, but that they exist in that narrow space where confidence remains high, yet certainty becomes just a little less absolute. In most areas of established science, especially those built over decades of observation and experimentation, there is a strong sense of reliability. The models work, the predictions align, the framework holds together. Cosmology, in many ways, has reached that level of maturity. The large-scale structure of the universe, the expansion of space, the life cycle of stars, these are not guesses. They are supported by extensive evidence. And yet, Webb is operating at the very edges of that framework. It is observing conditions that are more extreme, more distant, and more ancient than anything we have previously studied in such detail. And at those edges, even well-established models begin to show their limits, not because they are wrong, but because they were never designed to operate with complete precision under those conditions. This is where uncertainty naturally increases. But not all uncertainty is the same. There is the kind of uncertainty that comes from lack of data, and then there is the kind that comes from new data, data that is precise, but difficult to interpret within existing frameworks. Webb is giving us the second kind. And this creates an interesting dynamic, because on one hand, the quality of the data is higher than ever before. The sensitivity of the instruments, the clarity of the observations, the depth of the field, everything points toward increased confidence in what we are detecting. But on the other hand, interpreting that data requires us to apply models that may not yet fully account for what we are seeing. So confidence in observation increases, while certainty in interpretation becomes more nuanced. This is not a contradiction. It is a natural stage in the progression of knowledge, but it does create a subtle shift in how we think about discovery, because instead of moving from uncertainty to certainty, we are sometimes moving from broad certainty to detailed uncertainty. We know the general structure of the universe, but as we examine it more closely, the finer details become more complex, and Webb is accelerating that transition. There is also another layer to this idea, because uncertainty in science is not something to be avoided. It is something to be measured, quantified, and understood. Every observation made by Webb comes with error bars, confidence intervals, and statistical significance levels. These are not signs of weakness, they are indicators of precision. They tell us how much we can trust a result, and how much room there is for alternative interpretations. And when Webb produces results that sit near the edge of those confidence levels, it invites careful attention. Not immediate conclusions, but deeper analysis. For example, when a distant galaxy appears unusually bright or massive, scientists do not immediately declare that our models are incorrect. They examine the uncertainties. Could the brightness be affected by lensing? Could the distance be slightly misestimated? Could the stellar population be different from what we assumed? Each of these possibilities is explored, quantified, tested, and over time, as more data is collected, the uncertainty narrows. But during that process, there is a period where multiple interpretations remain plausible. And this is where Webb currently sits, not in a state of confusion, but in a state of active refinement, where observations are clear, but their implications are still being worked out. There is something quietly important about recognizing this, because from the outside, it can sometimes feel like science is expected to provide definitive answers, clear conclusions, final explanations. But in reality, science often operates in this intermediate space, where evidence is strong, but interpretation is still evolving. And Webb, by pushing the boundaries of observation, is naturally expanding that space. There is also a broader implication here. Because as our tools become more advanced, as our observations become more precise, the nature of uncertainty itself changes. It becomes less about whether something exists and more about how it behaves. Less about whether a model is correct and more about how complete it is. And this is a more subtle but more challenging kind of question, because it requires us to refine rather than replace, to adjust rather than overturn, to deepen our understanding rather than simplify it. And this process takes time. It requires multiple observations, independent verification, theoretical development, and careful analysis. Webb is only at the beginning of this process. Its data is still being interpreted, its implications still being explored. And that means we are currently in a phase where questions are expanding, even as answers are being refined. But there is something quietly reassuring about that, because it means that science is working exactly as it should, not rushing to conclusions, not forcing data to fit expectations, but allowing observations to guide understanding, even when that understanding becomes more complex. So as we continue to follow Webb's discoveries, it becomes less about looking for definitive answers and more about observing how the balance between confidence and uncertainty evolves. Because that balance is where real progress happens, not at the extremes, but in the space between them. And Webb, in its quiet, distant orbit, continues to operate within that space, collecting data that is both precise and, in some ways, still open to interpretation. Data that strengthens what we know, while gently expanding what we don't. And perhaps that is the most important takeaway of all. Not that the universe is uncertain, but that our understanding of it is always in motion, refining, adjusting, becoming more detailed with each new observation. So the question becomes, as Webb continues to reduce uncertainty in some areas and reveal it in others, what will that balance look like as the picture becomes clearer? As we continue to move further into this slow and thoughtful exploration, there is one more layer of the James Webb Space Telescope that begins to feel increasingly significant. And that is not just what it reveals about the universe, but how it subtly changes the way we frame reality itself. Because when you look far enough, deep enough, and precisely enough, you are not just gathering information, you are reshaping the context in which that information exists. Up until recently, much of our understanding of the universe has been built in stages. First, we understood our planet, then our solar system, then our galaxy, then the larger structure of the cosmos. Each layer added scale, complexity, and a deeper appreciation for how small our immediate surroundings are compared to the vastness beyond. But Webb introduces something slightly different. It doesn't just extend our view outward, it compresses time and space into a single frame of reference. When Webb captures a deep field image, what we are seeing is not a snapshot of a single moment. It is a layered view of different points in time, all overlapping. Some galaxies in that image may be relatively nearby, their light having traveled only hundreds of millions of years. Others may be so distant that their light began its journey more than 13 billion years ago. So in one image, we are seeing multiple eras of the universe simultaneously. And this has an interesting effect on how we think about reality, because it challenges the intuitive idea that we are observing a single, unified present. Instead, we are observing a kind of temporal mosaic, a collection of moments stitched together by the finite speed of light. This is not a new concept in physics, but Webb makes it more tangible, more immediate. It allows us to see quite directly that what we call the universe is not a static object, but a dynamic, evolving system where every point we observe exists at a different stage of its own history. And this leads to a subtle but important realization. When we talk about understanding the universe, what we are really doing is reconstructing a timeline from fragments that are all observed in the present, but originate in the past. And that reconstruction depends on our models, our interpretations, our assumptions about how time, space, and light interact. Webb, by extending the range of those fragments, is giving us more pieces of the puzzle. But it is also making the puzzle more complex. Because as we add more pieces, we begin to notice that some of them don't fit together as neatly as we expected. Not in a way that breaks the overall picture, but in a way that suggests the edges are more intricate, more detailed than we previously understood. There is also another dimension to this idea. Because when we observe distant galaxies that appear more developed than expected, we are not just questioning models of galaxy formation. We are, in a subtle way, questioning how quickly complexity can emerge in a system governed by the laws of physics. And that question extends beyond cosmology. It touches on broader themes: how structure forms, how systems evolve, how order emerges from initial conditions. In the context of the universe, these processes are governed by gravity, thermodynamics, and quantum mechanics. But the underlying question remains the same. How does complexity arise, and how quickly can it do so? The mainstream view provides a clear framework. Given enough time, simple systems can evolve into complex ones through well-understood processes. Stars form, fuse elements, explode, and seed new generations. Galaxies merge and grow. Structures emerge gradually. But Webb's observations suggest that, at least in some cases, this process may occur more rapidly or efficiently than expected. And that invites a deeper level of inquiry, not about whether the laws of physics are correct, but about how those laws manifest under different conditions. Because the early universe was not just a smaller version of the present universe, it was denser, hotter, more uniform in some ways, yet more dynamic in others. And under those conditions, processes may unfold differently. So when Webb shows us early complexity, it may not be surprising in a fundamental sense, but it may be revealing nuances in how those processes operate. And those nuances matter, because they influence how we understand everything that follows. There is also a philosophical layer here, one that remains grounded, but worth acknowledging. Because as we reconstruct the history of the universe from light that has traveled billions of years, we are, in a sense, building a narrative. A narrative that connects observations across time and space into a coherent story. And like any narrative, it depends on interpretation, not in a subjective sense, but in the sense that we are choosing models, frameworks, and assumptions that allow us to connect the data points. Webb is adding new chapters to that narrative, but it is also prompting us to revisit earlier ones, to see if they still align with the new information. And sometimes, when you revisit a story with new details, you begin to notice things you didn't see before, connections that weren't obvious, patterns that weren't clear, or small inconsistencies that invite a closer look. This is not a flaw in the story. It is a sign that it is becoming more complete. So as we continue this journey, it becomes less about seeking a final, definitive picture of the universe, and more about understanding that the picture itself is always evolving, refined by new observations, shaped by better instruments, adjusted by deeper analysis. And Webb, in its quiet, distant position, is playing a central role in that process, not by providing all the answers, but by expanding the scope of the questions. And perhaps that is what makes this moment so interesting. Because we are not just observing the universe more clearly, we are beginning to understand how our perspective of it is constructed, how time, light, and interpretation come together to form what we call reality. And as that understanding deepens, the line between observation and interpretation becomes just a little more visible, not blurred, but understood. And in that understanding, there is a kind of clarity, not the clarity of final answers, but the clarity of knowing where the boundaries of our knowledge currently lie, and where they might begin to shift next. So as Webb continues to collect light from across the vastness of space and time, it is also, in a quiet and steady way, reshaping how we think about the universe itself, not just as something we observe, but as something we are still learning how to understand. As we continue this steady descent into the deeper layers of understanding, there is another aspect of the James Webb Space Telescope that begins to feel almost philosophical, yet remains firmly grounded in science. And that is the idea that, as our observations become more advanced, the distinction between what is known and what is assumed becomes more visible. Not because assumptions are incorrect, but because they are finally being tested in ways that were not previously possible. For decades, much of cosmology has operated with a set of foundational assumptions that are well supported, but not always directly observable in every context. Concepts like cosmic inflation, dark energy, and the uniformity of physical laws across the universe are central to how we interpret data. These ideas are not arbitrary. They are based on strong theoretical and observational evidence. But Webb is now operating at a scale where those assumptions are being applied under conditions that are more extreme than ever before. And this is where something interesting begins to happen, because when an assumption works well within a certain range, and then begins to show small inconsistencies at the edges of that range, it doesn't necessarily mean the assumption is wrong, but it does mean we begin to examine it more closely. Take, for example, the concept of cosmic inflation. This idea suggests that the universe underwent a rapid expansion in its earliest moments, smoothing out irregularities and leading to the large-scale uniformity we observe today. It explains why the universe appears relatively homogeneous on large scales, while still allowing for the small fluctuations that eventually led to galaxy formation. Inflation is a powerful concept. It solves multiple problems within cosmology and aligns well with observations of the cosmic microwave background. But it is also a theory that operates at an energy scale far beyond what we can directly test in a laboratory. So when Webb observes structures in the early universe, galaxies forming, matter clustering, it is, in a sense, providing indirect tests of how those initial conditions played out over time. And if those structures appear slightly different from what our models predict, it raises a question about whether our understanding of those initial conditions is fully complete. Not incorrect, but perhaps not fully detailed. There is also the concept of dark energy, which is used to explain the observed acceleration of the universe's expansion. Like dark matter, dark energy is not directly observed. It is inferred from the behavior of distant galaxies and the expansion rate of space. It plays a crucial role in our current model of the universe, but its nature remains largely unknown. And Webb, by contributing to measurements of distant galaxies and cosmic expansion, adds to the dataset that informs our understanding of dark energy. If subtle discrepancies emerge in how galaxies are distributed or how they evolve over time, they could, in principle, influence how we interpret the role of dark energy. Again, not in a dramatic way, but in a way that encourages refinement. And this brings us to a broader realization. Because science often relies on layers of understanding, at the surface we have observations, data collected by instruments like Webb. Beneath that, we have models, frameworks that explain how those observations fit together. And beneath that, we have assumptions, foundational ideas that shape how those models are constructed. Most of the time, these layers align smoothly, but when new data arrives that doesn't fit perfectly, it can create a subtle ripple through those layers, not breaking them, but revealing where they might need adjustment. And Webb, by pushing the boundaries of observation, is naturally interacting with all three layers. It provides new data, it tests existing models, and indirectly, it touches on the assumptions that underpin those models. There is something quietly powerful about that, because it means that Webb is not just contributing to one area of science, it is influencing the entire structure of how we understand the universe, but it does so gradually, carefully, without forcing conclusions. And this is where the tone of this exploration remains consistent. We are not here to suggest that foundational ideas like inflation or dark energy are incorrect. They remain the best explanations we have, supported by extensive evidence. But we are also recognizing that as new data becomes available, those explanations may become more detailed, more refined, or in some cases, adjusted in subtle ways. And that process is not a sign of weakness, it is a sign of progress. Because the goal of science is not to arrive at a final, unchanging answer. It is to continually improve our understanding, to move closer, step by step, to a more complete picture. And Webb is helping us take those steps by extending our reach, by increasing our precision, by revealing details that were previously beyond our ability to observe. So as we continue, it becomes less about questioning what we know, and more about understanding how what we know is constructed, how observations, models, and assumptions interact, and how new data can subtly reshape that interaction. Because sometimes, the most important discoveries are not the ones that introduce entirely new ideas, but the ones that refine the ideas we already have, the ones that reveal nuance, the ones that add depth, and the ones that remind us that even our most confident understanding exists within a framework that is always, quietly, evolving. So as Webb continues its work, observing the distant universe, collecting data, revealing patterns, it is also, in a way, illuminating the structure of our own knowledge, showing us not just what we understand, but how we understand it. And perhaps, as that structure becomes clearer, we will begin to see not just the answers more clearly, but the questions that guide us toward them. As we continue toward the final stages of this quiet exploration, there is one more dimension of the James Webb Space Telescope that begins to settle into focus, and it is perhaps the most subtle of all. Not a specific discovery, not a single inconsistency, not even a pattern across data, but something more foundational. The realization that, as our ability to observe the universe improves, the nature of explanation itself begins to shift. Because for most of scientific history, explanation has followed a familiar path. We observe something. We build a model to describe it. We test that model. And over time, as evidence accumulates, the model becomes more refined, more complete, more reliable. And for many aspects of the universe, this process has worked extraordinarily well. We understand the life cycle of stars. We understand the behavior of gravity on large scales. We understand the expansion of the universe. These are not mysteries in the traditional sense. They are areas where our models align closely with observation. But Webb is now operating in a regime where explanation becomes more layered. Not because we lack data, but because we have so much data, and it is so detailed, that multiple explanations can sometimes coexist within the same observation. And this is where things become quietly interesting. Because when Webb observes a distant galaxy that appears more massive than expected, there isn't just one possible explanation. It could be that star formation was more efficient. It could be that we are misestimating the galaxy's mass. It could be that the initial conditions of the universe allowed for faster structure formation. Or it could be a combination of all three. Each explanation fits within the broader framework of physics. Each is plausible, and each can be tested, but not always immediately. So instead of a single definitive answer, we have a set of competing interpretations. And over time, as more data is gathered, one interpretation may become more likely than the others. But during that process, there is a period where multiple explanations remain valid. And this represents a subtle shift, because it means that explanation is no longer always about finding the answer. Sometimes it is about understanding the range of possible answers and narrowing that range through careful observation and analysis. This is not uncertainty in a negative sense. It is a more refined form of understanding, one that acknowledges complexity, one that allows for nuance, and one that evolves as new data becomes available. Webb, in this sense, is not just providing answers. It is expanding the space in which answers can exist. And that space, while grounded in evidence, is not always simple. There is also something else that emerges from this. Because when multiple explanations are possible, the role of assumptions becomes more visible, not as hidden biases, but as necessary starting points. Every model we use is built on certain assumptions about initial conditions, about physical laws, about how different processes interact. And most of the time, those assumptions work extremely well. But when Webb presents us with data that can be interpreted in multiple ways, it invites us to revisit those assumptions, to examine them more closely, to ask whether they are as complete as we believe. Again, not to discard them, but to refine them. And this brings us to a kind of quiet equilibrium. Because on one side, we have a strong, well-supported framework of understanding. On the other, we have new data that introduces subtle complexity. And between them, we have a process of continuous refinement, not dramatic, not disruptive, but steady. And perhaps that is the most important realization of all, because it reminds us that science is not a fixed body of knowledge. It is a process that adapts, evolves, and becomes more detailed over time. And Webb is accelerating that process, not by overturning what we know, but by adding depth to it, by revealing details that require us to think more carefully, to interpret more precisely, to consider multiple possibilities at once. There is also a certain calmness in that idea, because it means that not knowing something completely is not a failure. It is a stage, a necessary part of understanding something deeply. And Webb, by pushing us into that stage across multiple areas of cosmology, is not creating confusion. It is creating opportunity. Opportunity to refine, opportunity to connect ideas, opportunity to build a more complete picture of the universe. So as we approach the final part of this journey, it becomes clear that Webb's greatest contribution may not be any single image, any single discovery, or any single insight. It may be the way it reshapes how we approach understanding itself, moving us from simple explanations to layered ones, from certainty to carefully measured confidence, from isolated observations to interconnected systems. And in doing so, it invites us to engage with the universe in a different way, not just as observers, but as participants in an ongoing process of discovery, a process that is still unfolding, one observation at a time. So the question that remains is not just what Webb will discover next, but how those discoveries will continue to refine the way we think, the way we interpret, and the way we understand the universe as a whole. And now, as we ease into the final stretch of this journey, there is a certain stillness that settles over everything we've explored, not because the questions have been answered, but because we've begun to understand the shape of them. The James Webb Space Telescope, in all its precision and complexity, has not handed us a finished picture of the universe. Instead, it has done something quieter, something more enduring. It has shown us where the edges of that picture begin to soften, where certainty gives way to careful interpretation, and where observation invites deeper thought rather than immediate conclusion. If we step back and look at the full arc of what we've examined, a pattern begins to emerge, not just in the data Webb provides, but in how that data interacts with what we already believe to be true. We started with the idea that Webb confirms much of our existing cosmological framework, and it does. The expansion of the universe, the formation of galaxies, the chemical evolution of matter, these are not being overturned. They remain the foundation. But layered onto that foundation, Webb has introduced nuance, galaxies that appear earlier than expected, but not impossibly so. Chemical signatures that suggest rapid enrichment, but within the bounds of known physics. Patterns that seem consistent, yet slightly more complex than predicted. None of these observations break the model, but together, they gently press against it. And that pressure is where understanding begins to deepen, because science does not move forward only when something is proven wrong. More often, it moves forward when something is shown to be incomplete, when details emerge that require refinement, when patterns appear that weren't fully anticipated, when assumptions, even strong ones, are revisited with new data in mind. And Webb, in its quiet orbit far beyond Earth, is contributing to that process in a continuous, steady way. It is collecting light that has traveled across billions of years, carrying with it fragments of a story we are still assembling. Each photon, each spectral line, each faint structure in a deep field image becomes part of that story. Not a final answer, but a piece of a much larger puzzle. There is something almost meditative in that realization, because it reminds us that the universe is not something we can fully capture in a single moment of understanding. It unfolds gradually, revealing itself layer by layer, as our ability to observe and interpret improves. And Webb represents a step in that unfolding. Not the final step, but a significant one. It has extended our reach further than ever before, not just in distance, but in depth of analysis. It has allowed us to examine the early universe with a level of detail that was once unimaginable. It has connected different areas of study, cosmology, astrophysics, planetary science, into a more unified picture. But perhaps most importantly, it has reminded us of something fundamental. That observation and understanding are not the same thing. We can see further. We can measure more precisely. We can detect signals that were once beyond our reach. But understanding takes time. It requires interpretation, refinement, comparison, and sometimes reconsideration. And that process cannot be rushed. So as we reflect on everything Webb has shown us, the early galaxies, the chemical signatures, the subtle inconsistencies, the emerging patterns, it becomes clear that we are not at the end of a discovery. We are at the beginning of a deeper phase of understanding, a phase where questions become more precise, where models become more detailed, where assumptions are tested not in broad strokes, but in fine detail. And there is something quietly exciting about that, because it means that the universe still holds complexity that we have yet to fully grasp, not in a mysterious, unknowable way, but in a way that invites continued exploration. Careful, grounded, thoughtful exploration, the kind that doesn't rush to conclusions, but allows them to emerge naturally from the data. And as Webb continues its mission, year after year, collecting more light, more data, more clues, that process will continue. Patterns will become clearer. Uncertainties will narrow. Some questions will find answers, and others will deepen. Because that is the nature of understanding at this scale. It is not a straight path from unknown to known. It is a gradual expansion, where each answer reveals new layers of complexity, and each observation adds to a picture that is always, quietly, evolving. So perhaps the most fitting way to end this exploration is not with a conclusion, but with a perspective. That what we are witnessing through Webb is not just a clearer view of the universe, but a clearer view of how knowledge itself unfolds, step by step, observation by observation, refinement by refinement, and somewhere in that process, between what we know and what we are still learning, there is a space, a calm, thoughtful space, where curiosity remains open, where questions are allowed to exist without immediate answers, and where the universe is not something to be solved, but something to be understood, slowly, carefully, and with a sense of quiet wonder. And maybe that's the real secret, hidden within everything Webb is showing us. Not just the distant galaxies, not just the early universe, but the realization that the deeper we look, the more we are invited to think, not in certainty, but in understanding. And that understanding is still unfolding. And for now, that's where we leave it. A telescope quietly watching, a universe slowly revealing, and a story still being written.